Okay, so today we're going to be talking about cycloalkanes, so cyclic systems, and conformational analysis for cyclic systems. So we previously discussed open chain or straight chain compounds, but most organic molecules, such as the prostaglandins, which are quite famous molecules, have cyclic systems with stereochemical information. So let's define some of our terms here. So cycloalkanes are saturated cyclic hydrocarbons. So they have the general formula of CnH2n. So the main indicator that you have a cycloalkane instead of a normal straight chain alkane is that you will have 2 less hydrogens than normal. Now, the way that cycloalkanes are named, they're named exactly like your straight chain alkanes, except with a cyclo prefix. So for example, cyclopropane, so prop is 3 carbons. Cyclobutane, the but prefix corresponds to 4 carbons. And for cyclopentane, the pent prefix corresponds to 5 carbons. Now, probably the most interesting ring system and one of the most common in terms of natural products, pharmaceuticals, and other interesting biological systems are cyclohexane systems. So hex corresponds to 6 carbons. So we've seen and we've named cycloalkanes before. What we're now going to focus on is the process for describing the stereochemistry of these cycloalkanes and analyzing their different conformations. So let's talk a little bit about that. Let's talk first about naming conventions for cycloalkanes. We've seen a little bit of this in the nomenclature chapter, but let's just review some of the numbering rules. So they're named same as the straight chain alkanes, except you have to include the cyclo prefix. As a general process for naming these cycloalkanes, first and foremost, we're going to find the parent chain, the chain with the largest total number of carbons in the ring. And then you're going to number your substituents by positioning them at the lowest carbon numbers. So, for example, if we look at 1,3-dimethyl cyclohexane, we start counting at position 1 for one of our methyl groups. It doesn't matter which one. Now we have a choice. We can either count clockwise, or as an alternative, we can count counterclockwise. Let's entertain the possibility. What happens if we count counterclockwise? So we end up with the following numbers: 2, 3, 4, 5. So if we have a choice between counting clockwise and counterclockwise, if we count clockwise, so if we count clockwise around our ring, we end up with 1 and 3 for our substituent carbon numbers. If we count counterclockwise, so if we count counterclockwise, we end up with the numbers 1 and 5. And as we can clearly see, if we count in the clockwise direction around our ring, we end up with lower carbon numbers. So we're going to use the clockwise numbering method in this case. In other examples, you may have to count counterclockwise. The key thing is you count your carbons in your ring to give you the smallest carbon locant numbers. Everything making sense so far? If there are any questions, don't be shy to type in the chat. I am checking the chat right now. I don't see any messages in the chat, but please don't be shy, or please don't be shy to unmute and ask a question. If not, let's move on to some additional examples. So let's look at the next system. So in this case, we have multiple different substituents. So we have a methyl group, we have an ethyl group, And we have another methyl group. Okay. So just like before, when we dealt with straight chain alkanes, we want the lowest numbers for each of our substituents. So when we choose our counting method, we want to generate a counting method that has the lowest number at every single location possible. Okay, so obviously we're going to start counting at one of our substituents. Now, if there were only the methyl group and the ethyl group, we'd prefer to start placing the lowest number at the ethyl group. But since we have 3 substituents, we're going to want to find a counting method that gives us the lowest number at each location. Okay, so let's show an example here, and let's first entertain the correct solution. So we start counting. Our methyl is at carbon number 1. Our ethyl is at carbon number 2, and our second methyl is at carbon number 4. Now we are counting counterclockwise in this case. The reason being, if we tried to count clockwise from our methyl group, let's show that. 1, 2, 3, 4, 5, 6, 7, we'd end up with larger locant numbers. Okay. Let's entertain our other possibilities. So let's suppose we want to give the ethyl group the lowest possible number. So let's put the ethyl at the 1 position. So the ethyl is at carbon number 1. Now we have a choice between counting clockwise versus counterclockwise. And if our goal is to assign the lowest carbon number at every position, we'd want to put our methyl group at the lowest possible number, which would be carbon number 2. Now, all seems fine and well so far. If we didn't have this methyl group, if this methyl group didn't exist, this counting method would be preferred. However, because we have another methyl group in our molecule, if we continue counting around the ring, we end up with a methyl group at carbon number 6. And if we compare our carbon numbers, if we compare 6 and 4, we can clearly see that 4 is a lower carbon number, so this method wins out. Now let's entertain the other possibility. Let's suppose we start counting at the topmost methyl group. So we assign carbon number 1 to our topmost methyl group, and we're going to count clockwise to avoid the same dilemma that we encountered earlier. And our ethyl group ends up, our ethyl group ends up at carbon number 3. Now, if we compare our carbon numbering, we can clearly see that 3 is greater than 2. So this method of counting gives us large carbon locant numbers, so is not preferred. Okay. So this looks very familiar to what we dealt with when we were naming linear alkanes. And if we need some review on that, I posted some practice assignments on Canvas. Now, this is nice that we've gone through a few examples, but let's try next to discuss a critical aspect of cycloalkane stereochemistry, and a key difference between cyclic versus acyclic systems. So let's keep the naming rules in the back of our head. We'll be using them later on in this chapter, but let's now focus on a key aspect of this chapter, which is cis-trans isomerism in cycloalkenes. So first and foremost, cycloalkanes are less flexible than their open chain alkanes. One consequence of this, and one reason for this, is that the ring structure prevents free rotation of the single bond. So for example, when we're looking at Newman projections, we can clearly rotate about our carbon-carbon bond with no issue for our normal alkane. However, when we deal with a cyclic system, and you try to rotate about your carbon-carbon bond, if you make a model of, for example, cyclopropane. So let me make a sample model of cyclopropane really quickly for everyone to see. It's a super strained system. Okay, so here's an example of cyclopropane. Now, if I try to rotate my carbon-carbon bond, it's quite difficult to rotate the carbon-carbon bond without breaking a carbon-carbon bond. Cyclic systems are a lot less flexible. And as a result, when we think about our substituents, the relative location of our substituents in a cyclic system is a lot more fixed. So the main thing I want you to take away from this idea, from this demonstration with our model kit, is that cyclic systems are more rigid. However, there are still multiple accessible conformations. For which structure? Oh, the cyclopropane right here. Let me check the camera view. Okay. How about now? Does that look okay? This is chapter 4. We're currently on page 4 of chapter 4. Okay, perfect. So if we try to rotate about our carbon-carbon bond, you can see that this cyclic system is a lot more rigid. There's a lot less conformational freedom. And I'll be pulling up the back cam in a moment once we do a few problems. So one consequence of the fact that these cyclic systems are substantially more rigid, one moment, is that when we look at cycloalkanes, they have two visible faces when viewed edge-on. And this in turn leads to a phenomena known as stereoisomerism, where we have compounds which have their atoms connected in the same order, but they differ in 3D orientation. So the arrangement of our substituents is different in three-dimensional space. So when we have substituted cycloalkanes, we can observe cis-trans isomerism. So for example, if we looked at 1,2-dimethyl cyclopropane, so let's draw out what this structure looks like. So we have a methyl group at carbon 1 and a methyl group at carbon 2. Now, this structure that we've currently drawn is not particularly descriptive of the three-dimensional arrangement of these methyl groups. So let's try to describe each of our stereoisomers, each of our arrangements of these methyl groups in 3D space. So the first isomer that we're going to look at is the cis isomer, where the substituents are on the same face of our cyclopropane ring in this case. So you can clearly see from edge on, there's a top face and a bottom face of our cyclopropane ring. So as we can clearly see, our methyl groups are pointing up towards the top face, and both of these methyl groups are on the same top face of our molecule. So if we look at this model to the right, both of our methyl groups are pointing up. We'll learn later on in this chapter that and as we'll discuss in chapter 5, that both of these methyl groups would get a wedge, where this wedge is telling us that these methyl groups are pointing up out of the page towards us. Now let's look at our alternative stereoisomer. Let's look at our alternative stereoisomer. So the trans stereoisomer, in this case, the substituents are on the opposite face. So we have our top face and we have a methyl group that is pointing up. Additionally, on our bottom face, we have a methyl group that is pointing down. So as everyone can see, the two methyl groups are on opposite faces of our cyclopropane ring. And the way that we'd see this if we were looking at a model is one of the methyl groups is pointing up and the other methyl group is pointing down. So if we were drawing in dash wedge notation, the methyl group pointing up would get a wedge, the methyl group pointing down would get a dash. You don't have to worry about the dash wedge notation just yet. I just wanted to help bridge that gap, as cyclopropane systems are really quite interesting to observe. Now, one thing that I'd like us all to just take a moment and appreciate is if we compare the amount of steric hindrance observed in these two stereoisomers. Would someone like to, and take a moment and type in the chat, would someone like to propose to me which of these two structures has our methyl groups closer together? Which of these two structures experiences the greatest amount of steric hindrance? And you're welcome to unmute. Perfect. I see a lot of reasonable responses here for the cis isomer. Yep, the first one. So as everyone can clearly see, in the first stereoisomer, both of our methyl groups are on the same face and they're in close proximity. So in general, what we observe when we have substituents is that for cyclopropane systems, the cis isomer has a lot of steric strain, and this is a very high energy ring. It's a very high energy system. Now, what we're going to do next is we're going to dissect some aspects of each of the rings and talk about different types of strain observed for ring and cyclic systems. Okay, so we've established the cis and trans notation. Let's now do a study and let's look at all of our common cycloalkanes, and what we're going to be focusing on are ideas of angle strain, steric strain, and torsional strain. So we've seen these last two terms before in our discussion of linear alkane conformations. Now, a new type of strain that's typically observed for cycloalkanes is called angle strain. And this is distortion of bond lengths and angles from our ideal bond angle. Now, let's just discuss really quickly. So if we have a tetrahedral carbon, such as in methane, for example, what would be the ideal bond angle? What's our ideal bond angle for an sp3 hybridized carbon? What's the ideal bond angle, average bond angle? About, and you're welcome to type in chat during this time. Yep, I see a lot of 109. So 109.5 degrees is our ideal bond angle for an sp3 hybridized atom. Wonderful. Now, if we think about cyclopropane for a moment, we're going to begin to notice a bit of a square peg and round hole problem. The bond angle for cyclopropane is about 60 degrees. So we have a clear mismatch between our ideal bond angle and the observed bond angle. Now, in order to remedy this problem for cyclopropane, our carbon-carbon bonds are going to do something that's really quite interesting. So in our cyclopropane system, the carbon-carbon bonds are going to bend outward from our internuclear axis. So if our cyclopropane, under ideal conditions, we'd have our carbon-carbon bond along the dotted line. Instead, our orbitals are going to overlap, and they're going to be bent outward from the ideal carbon-carbon bond axis. So our bonds are quote unquote bent outward. Now, taking a look at this orbital overlap, if we compare this overlap to our ideal carbon-carbon bond with ideal bond angles, would you expect the overlap observed in cyclopropane to be stronger or weaker than in a normal carbon-carbon bond? So would we expect the cyclopropane carbon-carbon bonds to be stronger or weaker than usual? Weaker, yep, exactly right. So because of the unique geometric requirements to have a 3-carbon ring, cyclopropanes are often destabilized as a result of this angle strain. We are bending our carbon-carbon bonds away from their ideal bond angle. Now, this is why cyclopropanes in particular are very high energy systems. Okay, so let's talk next about our good old friend steric strain. So I'm going to bring up the analogy that we've observed last chapter of our methyl-methyl. We call this a gauche system or a gauche interaction. And fundamentally, gauche interactions are steric interactions, steric strain. Our two methyl groups are brought into close proximity in 3D space, and you end up with a repulsive interaction. Now, as we discussed previously, this gauche interaction costs us around 4 kilojoules per mole for each gauche interaction. So these are non-negligible. Now, likewise, by the same token that we can draw Newman projections for acyclic systems, we can also draw Newman projections for cyclic systems. So if we think about our cyclopropane, for a moment, let's suppose we're looking at diethyl cyclopropane. Now, if we look down our carbon-carbon bond in cyclopropane, similar to how we generated a Newman projection, looking down our carbon-carbon bond in butane, we can begin to appreciate that cyclic systems, we also observe similar steric interactions. So our ethyl groups are traced onto our Newman projection. And as we can see, just looking at these two ethyl groups in space, using our Newman projection scaffolding, are these ethyl groups pretty close together in space? Would we expect to observe an ethyl-ethyl steric interaction? And you're welcome to type in chat during this time or unmute and share your opinion. Yep, I see a lot of yeses. So these ethyl groups take up space, and as a result, we end up with a repulsive steric interaction. Now, what's really interesting is for cyclopropane, now let's really put our thinking caps on here. What do we notice is really special about the relationship between our ethyl groups? So there's a special term that we use to describe the angle between these two ethyl groups. What do we call it when the angle between our substituents is 0 degrees? What do we call that conformation? Yep, I see a lot of eclipsed. And this is really important to understand why substituted cyclopropanes are so unstable. So if we look down here, torsional strain is our last major interaction that often results in destabilization of our ring systems, which are repulsions between groups as groups pass each other during carbon-carbon bond rotation. Now, for cyclopropanes, so in this case, so just looking at our hydrogens, and I'll draw it in the same side-on view so we can begin to see the massive problem in cyclopropanes. Now, one thing that we've discussed previously, and let me make a model just to show this to you. Let me make the model so everyone can see. And I'm going to share the front camera so we can both see what's going on. So I'm going to do a new share. So I'm just going to pause the share. One moment. Is everyone able to see the model on the camera? Okay, perfect. I see the view now. Okay, perfect. So we're looking down our carbon-carbon bond, and we notice very quickly that are hydrogens eclipsed in this situation? If we look down our carbon-carbon bond? Yep. Now, and here's the kicker for cyclopropanes. No matter how much I try to rotate my bond, I'm stuck. I cannot rotate out of this eclipse conformation. Cyclopropanes are quite unstable. So one key feature of cyclopropanes that I want you all to appreciate is that the bonds in cyclopropane are locked in an eclipsed conformation. They're rigid. And as a result, we're stuck with all of these H-H eclipsing interactions. And as we can see, these eclipsing interactions are quite destabilizing. This costs us about 4 kilojoules per interaction. So this really adds up if we have a ring full of hydrogen-hydrogen eclipsing interactions. So key takeaways: rings are rigid, and cyclopropanes experience a ton of torsional strain because they're locked in the eclipsed conformation. Any questions so far? Okay, let's keep going. This is just our overview of ring systems. So, just to really emphasize our distortion of bond lengths and bond angles from the ideal. So if we think about all of our smaller ring systems, you're often distorting your bond angles in order to accommodate your smaller ring size. Now, this strain is destabilizing. It raises the energy of our system. And as a consequence of that, strain in general increases the reactivity of a molecule. Now, it's really important that we don't just think of many of these systems as flat, because molecules will distort and adopt conformations to minimize strain, to minimize angle strain, minimize torsional strain, and minimize steric strain. So rings larger than 3 atoms are not flat. These cyclic molecules can assume non-planar conformations to minimize angle and torsional strain by quote-unquote puckering. So what we're really going to focus on are our larger ring systems now, our cyclobutane, pentane, and hexane. Okay, so just as a review, as a recap from our study of cyclopropane, we've established cyclopropane has bond angles of 60 degrees. So we have significant angle strain. Additionally, we know that cyclopropane has significant torsional strain as the bonds are locked in an eclipsed conformation. So we have these eclipsing interactions. Okay, so that's wonderful review of why cyclopropanes are relatively unstable. Let's now move and let's discuss cyclobutane. So cyclobutane has less angle strain. However, if we think about a flat cyclobutane system, if it's perfectly flat and we have all of our hydrogens aligned above and below the plane of our cyclobutane, what is a major problem with having, yes, I can do that. So I was wondering what the major problem would be with having a completely flat cyclobutane. So imagine we had a completely flat cyclobutane. What is an issue with that? What interaction do we see? And let's recall what we observed for cyclopropanes, and let's focus specifically on these hydrogens. What would happen if our cyclobutane is completely flat? And you're welcome to type, yep, and let's be more specific. What kind of, yes, exactly right. So if cyclobutane is completely flat, then all of our hydrogens would be eclipsed. Now, to minimize this torsional strain, as you even see from this depiction of cyclobutane, cyclobutane adopts a puckered conformation, where, in effect, 2 of our carbons are bent up, well, 2 of our carbons are bent down. In this way, if we look down one of our carbon-carbon bonds and we view our hydrogen-hydrogen interactions, this puckering has minimized our torsional strain. Okay, so this is why we've distorted from a planar system to minimize these eclipsing interactions. And this is a common theme you'll see again and again in cyclic systems. Okay, so just to reiterate, cyclobutane is bent out of plane. 1 carbon atom is about 25 degrees above the other. Now this bend increases angle strain, so it costs us some energy, but it decreases torsional strain tremendously. Okay, let's move on and let's talk about some more common systems. Cyclopentane. Now, because we only have 5 carbons, because it's a 5-carbon system, we have an average bond angle about of 108 degrees. So we have substantially less angle strain than cyclobutane. Now, again, just like before, we do not want completely flat cyclopentane. We don't want a completely flat cyclopentane. We want to minimize our torsional strain. And if cyclopentane was completely flat, we would of course run into a monstrous amount of torsional strain. So to alleviate this problem, cyclopentane adopts what is known as an envelope conformation, where one of our carbons is substantially bent out of the plane of the page. Now, again, why does this happen? Why does this happen? So if we look down one of our carbon-carbon bonds and we compare the relative position of these two hydrogens, are we closer to an eclipsed or a gauche-like arrangement? Or are we closer to a staggered-like arrangement? Are these hydrogens eclipsed or gauche-like? So I see a lot of people saying gauche. Yep, that's exactly right. So we have a wider bond angle, so we're developing approximately a 30 to 45 degree angle between our substituents, and as a result, we have minimized our torsional strain. Okay, perfect. Now, thankfully, in this class, we won't have to focus a ton on these smaller ring systems. They are important, but a lot of our conformational analysis will focus on this next ring system, which is the cyclohexane ring system. So if I had to put a star next to the one ring system that you should know in and out, not only for this class, but for future classes in biology, understanding how cyclohexane ring systems function and understanding cyclohexane stereochemistry is a critical foundation that we need to get away from this chapter. Okay, so the cyclohexane ring is really quite interesting. So I have made a model of a cyclohexane ring. And we'll be dealing with manipulations of this model kit later on in this class to help people visualize some of the drawings I'm going to show you. Now, a key feature of the just to go back to explain this gauche. So essentially the gauche conformation is when the substituents are separated. So the gauche conformation is when the substituents are separated by approximately a 60 degree angle. And gauche specifically refers to when you have bulky substituents. So for example, if we're looking at a Newman projection with a hydrogen, a methyl, and a hydrogen, if we had a methyl on the back carbon, our bond angle, our dihedral angle is 60 degrees, and our substituents are relatively close in space. They have a large amount of steric bulk, and as a result, these two substituents will repel each other, and we call this a Gauche interaction. This becomes more pronounced when you start to look instead of hydrogen with a more substituted cyclopentane system. So we'll see more of these Gauche-like interactions actually in our cyclohexane system. Now, one of the really beautiful things about the cyclohexane ring is that they're free of angle strain And they can adopt what are known as quote unquote chair conformations with negligible torsional strain. So one way that we can really start to visualize what's going on in these chair conformations and explain why these chair conformations are so low in energy. And the best way to visualize a chair conformation, we have alternating atoms in a common plane. So some of our atoms, some of our carbon atoms are up, the other set of our carbon atoms are down. Now, just like we can generate Newman projections, for linear systems, we can also generate Newman projections for cyclic systems. So what we're going to do is, given the chair conformation shown here, we are going to look down. We're going to look down the bond between carbon 5 and carbon 4. And we're going to look down the bond from carbon 1 to carbon 2. So, in essence, the view that I'm showing you from the camera, without this methyl group, the view that I'm showing you from this camera is the same view that you'd get if you looked down carbon 5 and you looked down carbon 1. So carbon 1 is right here, carbon 5 is in blue. And immediately we begin to see the hallmark of the Newman projection. So let's piece this together. So looking at carbon 5, looking at the blue carbon, we have a hydrogen on, well, the view from the camera is flipped, but we have a hydrogen currently on the right. Yep, so it's on the right here. We have a hydrogen pointing down, and we have our methylene, the CH2 group, on the left. Does that make sense so far? And you're welcome to put together a model kit using your model kit during this time. Now, let's focus on our back carbon. What do we see for this hydrogen right here? Is it pointing up or down, this carbon in the back? This is carbon 4 that we're looking at. And you can type in the chat during this time. Is the hydrogen on carbon 4? Yep, I see a lot of ups. That's exactly right. That's why we have this hydrogen here pointing up. We also have a hydrogen, right here on carbon 4 that's pointing to the right. And finally, if we look at the methylene all the way in the back, is the methylene up or down? Compared to this hydrogen, is this methylene up or down? Yep, I see a lot of downs. That's exactly right. Okay, perfect. So we have the tools needed to go from a model kit to a Newman projection for cyclic systems. And I really encourage you to play with the model kit and just sort of turn it around, manipulate it, so that way you can start to develop this 3D manipulation in your head and just using paper. Okay, perfect. Now that we've mapped on all of our different substituents, Newman projection style, if we notice, if we pay special attention, so let's just erase and let's just focus on our two hydrogens here. Are we in the staggered or eclipsed conformation? Are we in the staggered or the eclipsed conformation if we look at this Newman projection? And you're welcome to chat during this time. Yep, I see a lot of staggered. That's exactly right. So we're in the staggered conformation. And as a result, we have minimized our torsional strain. This is partly why the chair conformation is so low in energy. So a nice little trick, whenever I'm unsure if I have a chair conformation, what I like to do, let me point this towards the camera. What I like to do is just stare at my molecule, and I always make sure if I look down my carbon-carbon bonds that my hydrogens or my substituents are staggered. And the reason why it's staggered is all of our substituents, oh, sorry. Did someone have a question? Oh, so to answer the question, why is it staggered? So we don't have any bulky substituents, so there are no major gauche interactions, and our hydrogen substituents and all of our substituents are separated by a bond angle of at least 60 degrees. So just to draw that out. So we have a bond angle separation of 60 degrees, and our hydrogens are not bulky, so we can't have any gauche interactions at play. And all of our substituents, both in the front and the back, are separated by a dihedral angle of 60 degrees. So there is a wide separation of our substituents in three-dimensional space. So just to help everyone see what's going on here. So if there's a 0 degree dihedral angle, we call it eclipsed. If there is a 60 degree dihedral angle, we call it staggered. Except, and this is the one exception, we can have gauche conformations if there's a 60 degree dihedral angle if our substituents are bulky. So for example, if we have a methyl group in the back and a methyl group in the front, even though there's a 60 degree dihedral angle, we observe a gauche interaction because the methyl groups take up a large amount of space. Does that make sense? So if we look at our hydrogens, we have a 60 degree dihedral angle, and our hydrogens don't take up very much space. Now this distinction is really important because we'll actually observe a special type of gauche interaction in our cyclohexane ring. So it's the same dihedral angle, but the only difference is that the gauche interaction occurs if you have bulky substituents that are separated by 60 degrees. And it's mainly looking at the substituents and looking to see, are the substituents taking up enough space for there to be a steric interaction? Yeah, so they're very, very similar. If you have really bulky substituents, another staggered conformation that we see, that we specifically refer to when we have bulky substituents, is if we have a full 180 degree separation. So for example, for dimethylbutane, this 180 degree separation would be considered staggered. So gauche is a very specific case where your substituents are 60 degrees apart and have steric bulk. Does that make sense? Okay, perfect. So let's talk a little bit about how to draw a cyclohexane chair conformation. Let's talk about how to draw a cyclohexane chair conformation. And if you have a tablet, you can hit share screen and draw it out and I can check your work, or you can follow along with me on a piece of paper. So this is really basic, but it's really important that you draw proper cyclohexanes. So first and foremost, just to show you what a complete cyclohexane looks like. A complete cyclohexane looks something like this. And the process that I have, or that I've used to teach students how to draw cyclohexanes, is first and foremost, we draw two parallel lines. Okay, so each dot on the line is a carbon. Okay, next we're going to place our topmost carbon as a dot. So we have our two parallel lines, and we're going to place our topmost carbon as a dot. Then we connect our two parallel lines to our topmost carbon. So you should have something that looks like this so far. Next, we're going to place our bottommost carbon and connect the dots. So just to show the process one more time, just to show the process from start to finish, we draw our two parallel lines, we place our top carbon as a dot, and we connect the lines to the dot. We then draw our bottom carbon and we connect the lines to the dot. Let me draw this a little more stylistically. Now, it's just going to take some practice, and try just drawing out 10 or 20 cyclohexane conformation or cyclohexane sketches in the chair conformation just to get the hang of it, because it's really important that you correctly convey the location of substituents in this cyclohexane ring. Now, there are a few really important things to keep in mind here. These two vertical lines are going to be completely parallel. Additionally, our horizontal lines are also going to be completely parallel. And finally, our additional diagonal vertical lines are also going to be completely parallel. I know practice really makes perfect here, so you want to be comfortable drawing both chair conformations. So here's our first chair conformation, and I'd want you to try practicing drawing the second chair conformation. And the way you do that is you draw your parallel line. So let me show you what the second chair conformation looks like. It looks very similar, but there's a critical distinction between these chair conformations. And the way that you start this one is you draw your two parallel lines, pointing in the opposite direction, and you place your top dot and your bottom dot on the opposite sides. So does everyone notice how my top dot's now on the left and my bottom dot's now on the right? Now I connect the dots, and I have, let me try drawing that one more time just so everyone can see that a little more clearly. So top dot, bottom dot, connect the lines, and there we go. We have our other chair conformation. Practice really makes perfect. We're going to focus on drawing a ton of these throughout this chapter. I'm just going to check the time really quickly just to see. Okay, we still have some time. We're going to now analyze these chair conformations and show how to draw these chair conformations from bond line depictions. So, one thing that is critically important to observe, so if we look at our cyclohexane ring system, does everyone notice how we have some hydrogens that are both above and below the plane, the flat carbon plane of the page? Does everyone see the carbons pointing up and down relative to our carbon plane? Does everyone see these carbons up here and these, oh, sorry, these hydrogens up here and these hydrogens down here? Okay. So we call these hydrogens axial hydrogens because they're both above and below
Okay.
the ring axis. One moment. Oops. Sorry about that. Okay, so these hydrogens in red are known as the axial hydrogens because they're above and below the flat plane of our carbon ring. And just like in the Earth, the hydrogens that are parallel to the carbon plane are known as equatorial hydrogens. Now, as we notice in our cyclohexane ring, we have 6 axial hydrogens and 6 equatorial hydrogens. So one thing that I do want you to pay attention to is the fact that 3 of our axial hydrogens are axial, pointing up, and 3 of our axial hydrogens are axial, and are they pointing up or down? Yep, I see a lot of down. Just keep this in the back of your head, as this will be critically important when we start writing out these cyclohexane chair conformations from dash wedge notation. Okay, so if we observe our cyclohexane ring just head on from the bottom up, we can clearly see our axial hydrogens and our equatorial hydrogens. Okay. So each face of the ring has 3 axial and 3 equatorial hydrogens. So what do I mean by that? So let's take a look at our equatorial hydrogens for a moment. So just like our axial hydrogens, we have 1, 2, 3 that are equatorial, pointing down, and 1, 2, 3. So I'm going to put a star next to them. And these hydrogens are equatorial. So let's focus specifically on the hydrogens with the star next to them. Are they pointing up or are they pointing down? Are they pointing towards the top up portion? Yep, I see a lot of people saying up. Yep. So these are equatorial, pointing up. Okay, so this is really important. Half of our axial hydrogens are pointing up, half of them are pointing down. Half of our equatorial hydrogens are pointing up, half of them are pointing down. Okay, perfect. Now, let's talk a little bit about how to draw axial and equatorial hydrogens. So let's start with our, equatorial and axial. Okay, so the axial hydrogens are the hydrogens either above or below the plane of the page. They're on the vertical axis. So you notice how this hydrogen's on the vertical axis, this hydrogen's on the vertical axis. Comparatively, the equatorial hydrogens are on the horizontal axis. They're on the same plane or close to the same plane as our carbons in our ring. They're almost sitting on the equator. And if you view it from the perspective of the model, so like let's do a side-on view, the axial hydrogens, such as here and here, are pointing along the vertical plane. Yes, they'll always be 50% up and 50% down. So, sorry, let me get the view just right. So here are axial hydrogen, so here are axial hydrogens, which are pointing in the vertical plane, and here are equatorial hydrogens, which are aligned along the horizontal plane. And the way you can differentiate the substituents is basically looking at how the substituents are pointing. How do you determine which one goes up or down? Okay, so let's start with the axial. So we can clearly see that these hydrogens are pointing up, right? They're on the top half of our molecule. Likewise, if we focus, let's just focus on this equatorial hydrogen right here. Now, if we look at the bond, to that hydrogen atom. Whoops, one moment. Let me set something up here. Would you be able to erase your annotation? Oh, thank you. So if we look at so here's a quick trick, and we'll talk about this more in a later section, but if one of the hydrogens is pointing up, the other hydrogen attached to that carbon is pointing down. You can also tell if we look at the bond between our carbon and our hydrogen, if we draw an arrow across our carbon-hydrogen bond axis, is the bond pointing up or down? I know it's pointing to the right, but is it pointing up or down? What's the angle? Does it look like it's going up or down? And yep, exactly right. So then we can clearly see that this equatorial hydrogen is equatorial, pointing down. Likewise, if we look at this equatorial hydrogen, so we have an axial hydrogen pointing down, so this equatorial hydrogen is pointing up. We can see that if we look at our carbon-hydrogen bond, we can clearly see that the bond is angled up. Yep, that's one way of thinking about it, yep. The hydrogens that are pointing straight up or straight down are axial hydrogens, while the ones that are in the horizontal plane and slightly angled are equatorial hydrogens. Exactly right. Does that make a little more sense where we're getting this up and down notation? We're looking at the relative arrangement and orientation of our carbon-hydrogen bond in space. Okay, perfect. So let's talk a little bit about how to draw axial and equatorial hydrogen. So first things first, we start with our blanket scaffold, and then at each of our carbons, we fill in our axial hydrogens. So I like to think of it as I fill in my 3 axial hydrogens pointing up. Note, you fill in your axial hydrogens pointing up at every other carbon. Then we fill in our axial hydrogens pointing down at the other set of carbons. Okay, so you notice how we alternate with our axial hydrogens with 1 up, 1 down, 1 up, 1 down. Okay, now we're going to fill in our equatorial hydrogens. And a rule of thumb is that the arrangement of this bond, of this carbon-hydrogen bond, is going to be parallel to the carbon-carbon bonds in your cyclohexane ring. It doesn't actually, so it doesn't actually matter which carbon you start with for adding the axial up hydrogens, but as a rule of thumb, the carbon that's pointing up, I like to call 1, and the carbon that's pointing down, I like to call 4. I always like to start with my up hydrogen at carbon 1 for this chair conformation. So in general, you start at carbon 1. And we'll talk about how this works when we have our second chair conformation. Now, as we notice, we're filling in an equatorial hydrogen pointing down, so we can fill in our other equatorial hydrogens pointing down. So in this case, our carbon-hydrogen bond is parallel to our carbon-carbon bond. And then finally, our carbon-hydrogen bond is parallel to our internal carbon-carbon bond. So we filled in all of our hydrogens that are equatorial pointing down. Let's fill in our equatorial hydrogens pointing up. Okay, again, always make sure your carbon-hydrogen bonds, if they're equatorial, they're parallel to the carbon-carbon bond in the ring. So we filled in our equatorial hydrogens pointing up. So what I want us now to do is to take a moment and let's fill in just these cyclohexane outlines from scratch. These are similar outlines that you'd get on an exam. If I ask you to do a cyclohexane ring flip problem, I may have you just fill in this skeleton to save some time. You should know how to draw this cyclohexane chair conformation skeleton, but let's do one more repetition of drawing out our substituents. So I have carbon 1 and carbon 4. I'm going to start by putting all of my vertical axial hydrogens that are pointing up. Then I fill in my axial hydrogens that are pointing down. Then I fill in my equatorial hydrogens. Remember that we're always parallel to the carbon-carbon bond in the ring. Then I fill in my second set of equatorial hydrogens that are pointing up. Okay, now what I want everyone to do and what I want us to try is I want you to try to fill in the cyclohexane chair conformation on the right with axial and equatorial hydrogens. And I want you to then either bring the picture up to the camera and share a portion of your screen, or share a portion of your drawing that you've generated on your screen. Let's try that just to see how it works, and I'll give everyone a few minutes to fill in the cyclohexane chair conformation on the right, and then we'll come together to discuss in about, let's do it in about 2 minutes. And if anyone wants to share their picture, don't be shy and I can give you permission to share. And if you want me to check your work, you can share and I can take a look at it. Okay. Let me Okay, I think in the sharing options, you can hit share and then share screen. Let me see if that works. Let me see. Yep, that looks good. Oh. Yep, the ones that I see look perfect. Okay, so what I'm going to do is I'm going to convey the student responses to the class, so that way we can observe. So from the student responses, I'm just going to summarize the points that we've made. So we have carbon number 1 and carbon number 4. We're going to start placing our axial pointing up hydrogens on carbon number 1. Then we place our axial pointing down hydrogens on our alternate carbons. Then we fill in our equatorial hydrogens. Pointing down, and then we fill in our equatorial hydrogens pointing up. Perfect. So you should end up with something that looks a little bit like this. Now, one thing that I do want you to note in this is that when we have our carbon 1 and carbon 4 labeled in the following drawing, after a ring flip, carbon number 1 ends up here and carbon number 4 ends up here. So as you've noticed, we've exchanged our carbon number 1 pointing up for carbon number 1 pointing down. So this is building towards this idea of a ring flip, the fact that these two chair conformations can interconvert at room temperature. And as a consequence for that, one thing I want you to focus on is if we look at this axial hydrogen and we compare, so this is up axial, if we circle the same hydrogen that's pointing up, is this hydrogen on carbon 1 that's pointing up, is it axial or equatorial? And this is a really critical point here. Is this hydrogen axial or equatorial, this hydrogen that I've starred? And you're welcome to type in chat during this time. Is this hydrogen right here? Yep, exactly. So at carbon number 1, we went from a hydrogen that is axial pointing up, and then after our ring flip at carbon number 1, we have a hydrogen that's equatorial pointing up. Exactly. So a critical aspect of these two cyclohexane chair conformations, they can interconvert. And when they interconvert, the relative, so there aren't, there's no name for one versus the other, unfortunately. The way that we often distinguish these chair conformations is by designating one as the low energy or high energy. But there's no specific wording to describe one over the other. Because in some cases, the same cyclohexane chair can be drawn from multiple different perspectives. You can differentiate them if you designate the stereochemistry or if you designate the conformations based on energy. And that's the primary way that we'll distinguish different conformations based on saying low energy versus high energy. which is actually what we're going to focus on next class session. So to continue on and really to help us understand this key point, this is the last point for today, we're going to focus on the conformational mobility of cyclohexane. Now, remember how we talked about this idea that carbon-carbon bonds are rotatable? That's because the barrier to rotation is relatively low, that at room temperature, our molecules have enough energy to rotate about the carbon-carbon bonds. By the same token, the energetic barrier required for a change in conformation for a cyclohexane ring is low enough that it can undergo changes in ring conformation at room temperature, a quote-unquote ring flip. Now, when our cyclohexane, so the main reason why the hydrogen on carbon number 1 changed from axial to equatorial is that these two chair conformations are before and after a ring flip. And during a ring flip, all of your axial substituents are converted to equatorial substituents. And that's actually what we're going to talk about and expand on now. So, one way to help everyone see what's going on here is I always like to map my carbon number 1, which is the carbon that's pointing up, and carbon number 4, which is the carbon that's pointing down. Now, in a ring flip, carbon number 1 is being brought down and carbon number 4 is being brought up. Now, as a consequence of this, and it's really easy to see with a model, Okay, so here we go. So carbon number 1, which is yellow, is pointing up. Carbon number 4, which is blue, is pointing down. In a ring flip, I bring my yellow carbon down and my blue carbon up. And one thing that you begin to see, it's not just being turned upside down, it's when you physically try, when you start to undergo a ring flip, as you bring the yellow carbon up, and just watch really closely what happens when I move the yellow carbon, our other substituents change in position. So the real thing that's going on in the ring flip is as we bring one of our carbons up and the other carbon down, the relative positions of our axial and equatorial substituents change. So it's not like I'm turning this molecule upside down or anything. It's just as we move and we exchange the relative position of our carbon 1 and carbon 4, all of our other substituents flip from axial to equatorial. And I really encourage you to take the model and physically move carbon 1 up and move carbon 4 down, and you begin to see that the rest of the molecule begins to change in terms of which substituents are axial and equatorial as a result of this ring flip. So just to show that one more time, I'm going to bring my blue carbon up and my yellow carbon down. And I'm going to put a functionality. So you can see what happens. So let's pay really close attention. Let's pay really close attention to our yellow carbon. So our yellow carbon has an axial substituent, and our yellow carbon is pointing up. I'm going to bring my blue carbon up and my yellow carbon down. And now my question to all of you is, did this methyl group change from axial to equatorial? Yep, I hear some yeses. Yep. So it's not that the bonds are rotating. It has to do with the fact that all of our hydrogens are locked and will prefer to be in a staggered conformation. So as we undergo a ring flip and as we change the relative positions of our two carbons, in order to maintain that staggered conformation, our substituents will flip from axial to equatorial. So it's as the result of adjusting the relative position of our carbon-carbon bonds, the other carbon-carbon bonds change in relative position to one another. So in essence, carbon number 1 is being brought down, carbon number 4 is being brought up. And just from mapping, just to remember, carbon number 4 is now up and it's right here. Okay, now this is really important because I see students mistake the location of carbon 1 and 4 after a ring flip. So just to showcase this once again. So carbon number 1 is in yellow, carbon number 4 is in blue. I bring carbon number 4 up and bring carbon number 1 down. Now, one thing that I do want you to pay attention to, is that from our view perspective, the yellow carbon, which is carbon number 1, is now, from our view perspective, if we're mapping onto this chair conformation, carbon number 1 is now right here. Okay, let's show this one more time, as this is a really important idea. Okay, so we're looking at it from this perspective. Now I just want you to tell me, is carbon number 1, the yellow carbon, can you current, so let me position this. Okay, so is carbon number 1, the yellow carbon, is it in the front or in the back from our camera view? Is it in the front or in the back? Yep, I see a lot of backs. Okay, I'm gonna raise carbon number 4 and drop carbon number 1. Okay, now from our camera view, is our yellow carbon, carbon number 1, now in front? Or if we're looking at our from the view of a cyclohexane chair conformation, is carbon number 1 from our view, is it now in the carbon that's closer to us? Yes, okay. So our carbon has not changed in terms of its absolute connectivity, but it's changed if we're drawing out our chair conformations exactly like this. You need to make sure that carbon number 1 is this carbon right here, okay? So it's not like the carbon is magically migrating. It's just from our perspective, if we're keeping our perspective fixed, if we always want to draw our cyclohexane in a chair conformation, you need to make sure that you're mapping your carbons properly. Does everyone understand the mapping? So just one more time, carbon number 1, carbon number 4. At the end of our ring flip, carbon number 1 is here and carbon number 4 is here. Additionally, and this is really important, so our axial substituent on carbon number 1, our axial substituent pointing up after the ring flip is now equatorial, but is this substituent, is this red substituent that I circled, is it still pointing up? Is it still pointing up? So looking at our carbon substituent bond, yep. So it's equatorial pointing up. And that's another thing that you have to preserve. The stereochemistry, whether your substituent is pointing up or down, is preserved in a ring flip. So let's take a look at that one more time. So in this case, let's look at the equatorial substituent. It's equatorial, pointing down. So after a ring flip, we have a substituent that's now axial. And is it pointing up or down? Is it pointing up or down? This substituent in blue that I've circled on the right-hand side. Yep. It's axial, pointing down. Exactly right. So we've changed from axial to equatorial, but our stereochemistry, the relative position of our substituents, has not changed. Substituents that are down are still pointing down. Substituents that are up are still pointing up. Okay, now what's really important to note is that these two chair conformations are not always energetically identical. And what we're going to discuss next class session is how to assess the relative energies of each of our cyclohexane conformations and how to draw the lowest energy conformation. So that's all I have planned for today. I'll be saving and uploading this video. What we'll do is we'll take a short break, and then at 7 o'clock, we'll open up the lab interface. I'll talk a little bit about today's lab, guide you through the process for accessing the video recordings and answering any questions we have. Okay. So I'll give everyone a 10-minute break, and then we can, we'll start the Zoom meeting for the lab section then. So I'll be saving this recording and we'll resume in the lab session.